Today I'm bringing you guys to my PLTW again. Trying to get a couple of things in here. I'm not going to be able to teach everything I know, but I'm going to teach you a couple of things I think are useful, probably in life and stuff like that. And definitely later on. So courses right here, I click there, and then once I click there, I'm going to go to Principles of Engineering, just like you will. I have more stuff here than you do. Click Principles of Engineering, and when you do that, it'll bring you here. And on the side, I'm going to go to 2, or actually 2.1 right here, Aesthetics. And we're not going to do a career field description. We've talked about careers and already. Centroids, I'm going to skip that one. I think that's better to do in person. Beam deflection, actually they're all better to do in person because this one's way more fun in class. We actually take the 2x4s like this, and we actually lay them on there, and we stand on them, and we see how much they bend. We measure how much they bend, and then we change them and rotate them around this direction in this mode, and I'll talk about those two in a minute in class. But right now we're just going to learn about it right here, and I want you to learn some of these words and stuff like that. So first thing you need to learn is the difference between these two things. You get a 2x4 or 2x6. That means that the wood is 2 inches by 6 inches or 2 inches by 4 inches. Now in real life, if you were to measure it with a ruler, they won't be that. I just want you guys to know that. In real life, a 2x4 is 1.5 inches by 3.5 inches. So just take a half inch off. Take a half inch off both. So if it says it's a 2x4, it's really, take a half inch off both, it's really a 1.5 by a 3.5. You can measure them in real life if you want, but that's just the way it is. The reason being is when they're originally cut, they are cut 2x4, but then they're planed down by machines, kind of like to smooth off the edges and make sure they're straight and stuff. And by removing that extra material, they end up taking a 1/4 inch off of everything on all sides, and a 1/4 inch off all sides means a half inch total on each dimension. So a joist. If you push the force downward on a joist like this, that's called a joist. If you rotate the wood around this way and you stand on it this way, that would be called a plank. This is much, much weaker than the joist right here. So the joist is stronger. It's going to flex way less than a plank. So if you look up in your attic or underneath your flooring of a house that's above ground or anything like that, you'll see that there's tons of these joists. And then they do lay planks over them so that there's flat areas you can walk on, but there's going to be a bunch of joists underneath. That's going to give you the strength right here. This just gives you more area, of course, to play with, but this joist is what gives you the strength. Knowing the strength of a wood, plank, or joist, you do need to know this, the inertia, moment of inertia. You can calculate the moment of inertia using this equation. It's nothing crazy. There's a 12, always there, so no big deal. So really you just need to know two things, a base and a height. So that's all you got to do is to calculate it. So if you look, this one right here, so you're looking at this little side profile right here where I'm kind of moving my mouse. And the side profile, the base is this way, and the height is this way. So here we go, we got the base, this one's got a little base and a lot of height. Notice the height, so moment inertia, the more base you have, the more moment inertia you have. The more height you have, the more moment inertia you have, both. Except that h is cubed. So the height is way more important in the moment inertia. That's why this one's so much stronger. That height is cubed. So when I take these two numbers, the base and the height gets cubed, and this one's so high that this moment inertia becomes very strong. This one, the base is wide, but the height is very small, so when it gets cubed, it doesn't help much there. So, how do you calculate it out? Well, you just need to know the base and the height. And here we go, calculating it out. You do the math. It looks something like this. It's not crazy math. It's not. You just have to cube this one and then multiply it by this one. So if I were to do it on a calculator, I'm going to go down here and I just type in calculator, there we go. And I have a calculator. Does this have a cube function on it? I don't see one here. There's no cubed function. There's a squared right here, but there's no cubed. I wonder if I change my calculator to a scientific calculator, if I get one. Oh, look at that. I got a cubed now. So yes, a lot of scientific calculators, because there's a lot of cube functions, will have them. So just click here and change it to scientific, not a standard one. So scientific, there we go. So let's see if I get the same result. If I get 21 inches to the 4th power. That's the unit actually in the end, because you got to the 3rd power plus another power. These are all distances, all inches. So let me get this answer. So I'm going to do 5.5 but cubed. We should do the cubed first, 5.5, and then I'm going to cube it. There we go, it's a big number. And then I'm going to times it by 1.5, times by 1.5. I get 249 on top right here, but then I got to divide it by 12. So divide it by 12 equals, and I got 20.79, and that's what they got. They got 21. Why did they put 21? Remember, in science, there's no way that I can accurately say that this is the results, all this junk right here. For example, this is the 10th, the 100th, the thousandths, the 10,000ths, the 100,000ths. This is a millionths place right here. I can't say down to the millionths of an inch how accurate this is, because they didn't give me any accurate measurements. They only told me 5.5 and 1.5. That's it. So they gave me two numbers here, 1.5. I know it says 1.5, same thing. And they said 5.5. That's two numbers there, two numbers there. So my answer could only have two numbers right there. So my answer could only have these two numbers right there. So I can report that. But when we report this number, we should probably just look to see if this is high enough to round it, and it is. So we're going to say 21. You should do that in engineering and in science always. Report your number in what's called, what do they call that? I just blanked out, but it's significant digits. There you go. So in significant digits, we should actually look. In other words, those are significant. These ones are not significant. These are like, there's no way that I can say that that's how accurate this was. I don't have, they never gave me numbers that were that accurate, so I can't report accurate numbers. I can only report inaccuracies of up to 2 digits. So right there, 21. So I did get the right answer, 21. Not too hard there. So that was beam A. Beam B, they got 1.5. Let's see if I can get that same answer there. Beam B, let's clear this out. All right, whoops, clear. And I'm going to do the cube first, 1.5. So 1.5, and then I'm going to cube it right there. Click cube. Then I'm going to times it by 5.5. Times it by 5.5 equals, and I get this number on top. And remember, never round until you're all done, okay guys? So we do round, but we don't do it till the end. Divide it by 12, so divided by 12. And I get 1.54, blah, 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 blah. But remember, these are not necessarily that accurate. So let's see, I got two numbers here, 1.5, and I got 5.5. So there's only two numbers and two numbers. They didn't give me any real accurate numbers, so I can only report two numbers. So I'm going to report these two right here, and I'm going to report those two digits. And this one is not high enough to round this, so I'll just say 1.5, and that's what they got too. So look at that. I'm as smart as whoever wrote this. Anyway, so that's how you do it. It's not really hard. It's literally just two numbers. Just got to cube the one. You got to cube that one right here, then times it by the other number, then take that answer and divide it by 12. That's it. And then you got the what's called the moment of inertia. And that tells you how strong this thing is going to be. It tells you how strong it could be. Okay, but there's more to it. There's more to it. So how much is it going to flex? Well, the moment of inertia is very important in that, but that's not all. So now you want to know how it flexes, correct? Well, how it flexes depends on these things right here, like what it looks like on the side. We're only going to do simple ones like this and like this. We're not going to do I-beams. Although I-beams, for how much material you have, they're actually pretty strong, and that's why people use them. You save a lot of material right here, like if this was made out of metal. And you still have a small base and a huge height, and so they are very strong when you push down on them from up here, and you save money. So, but we're just going to do just straight blocks like that. Okay, so in other words, and I think if I remember right, this changes this number here. You see that 12 right there? That 12, depending on the shape right here. So since we're just using a plain shape, we're going to keep that 12, okay? Modulus of elasticity. That has to do with not the shape on the side, but just the material. Think about it. Wood, plastic, metal, steel, they would bend differently, wouldn't they? So we need to know that if we want to know how much this thing is going to bend. We need to know something called the modulus of elasticity. That just means how bendable is it. Okay? So here they listed two materials. They don't have metal, but they gave you Douglas fir and they gave you ABS plastic. So they give you a certain type of plastic and Douglas fir, and they give you the elasticity of both. This one is bendable, but not very much. It's a very big number, so it's not very bendable. This one, plastic, is more bendable. it's got a lower modulus of elasticity. So we definitely need to know that to calculate the how much it's going to bend. So how do you figure out how much something is going to bend? So I have this big piece of wood right here. See this black thing here? It's going to bend when I apply this F, this force on it, correct? Well, first off, I got to tell you that we're going to assume that we're always going to apply the force right in the middle of the support. So from here to here, we're going to apply the force right in the middle. You know, that depends on the different stuff. So we're going to assume the force is right in the middle. And here's the equation, and it'll tell you how much it bends, delta max. That means how much, the maximum amount it will bend. So like this number will be small, like let's say 0.5 inches or 1 inch. That's how far this will flex, okay? And it depends on this, 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 and this. 4 variables. Okay, what are they? Well, one, it depends on force. Of course, the harder I push, the more force, the more this is going to bend. So that makes sense. Bigger F, more bending, right? More flexing right here. L, it depends on this length. L, see L right here, this L? L, it depends on that. Yes, of course, if this was like only 1 foot long piece of wood and you tried to bend it, it would be hard to bend a 1 foot long piece of wood. But if I gave you a 10 foot long piece of wood and you pushed in the middle of it, it would bend a little bit more. So yes, that matters. In fact, by a lot. That's why it's L cubed. So the length matters. So we need to know the length of this piece of wood from here to here, from support to support. Not necessarily the length of wood, but the amount of wood that's not supported. So you see it's supported here and it's supported here. And we need to know that length. So that one right here. So how hard are you pushing? How long is this piece of wood? Times it, divided by this 3 things multiplied together. It's 48, E, and I. E is a modulus of elasticity. You just look at that. Honestly, you just look it up. You go, what is it? For Douglas fir, it was like 1.8 million or something like that. We put that in here. So the bigger this number, remember it's on the bottom of the equation, the bigger this number, the smaller this gets. So as this gets bigger, this gets smaller. So the stronger the elasticity, the smaller it's going to flex. That makes sense, okay? And then I is that thing right here, this moment of inertia, right here. See, it's I right here. So it's I, and remember I showed you how to calculate that. I even did it on a calculator. So of course, now the more I, the more moment of inertia, the stronger it is and the less it flexes. So this stuff right here is what's called inversely proportional. When these things on the bottom get bigger, this gets smaller. That's called inversely proportional. This stuff on top is called directly proportional. The bigger it gets, the bigger this gets. And once again, this is inversely proportional. The bigger any of these get, the smaller this gets, because it's on the bottom of the equation. You're dividing it and then it gets smaller. So that's only 4 things. That's the biggest equation you actually ever have to do freshman year, to be honest with you. This is the most work all my freshmen have to do mathematically. You put how much force you push down, times it by the length of this thing, but cube it, divide it by 48, that's always 48, times the modulus of elasticity, just look it up. What do we use in Douglas fir? So, you know, it's 1.8 million. And then, or if it's plastic or whatever, just look that number up. And then I, modulus of elasticity, you'll have to calculate that on the side somewhere, like I did above, right? You just kind of measure how wide it is and how tall it is, and you do the little math, divide it by 12 thing, and then you just put it in there, and that's it. That's not hard. It's, you know, it is math, and it scares people, but it's not that hard. You saw how easy it was when I did that one up there. So, could I show you guys how to do it? Well, this is kind of doing it for us. So here they put 250 pounds, and the cool thing is this is engineering. So in engineering we use imperial units, which means pounds and inches, where in science class you would never do that. You would use, instead of pounds, we'd use newtons. Instead of inches, we'd use probably centimeters or meters. All right. So and instead of PSI for pressure, we'd probably use pascals or something. But anyway, in engineering, we use this way. So you put 250 pounds, that's like my weight standing on this thing. Okay, I'm a little less than that. 250 pounds, you stand in the middle. You're using a 96-inch long beam, that's 8 feet. And then times it by, and then right here on the bottom, you take 48, you times it by this, 1.8 million. And that's just because Douglas fir right here is 1.8 million, okay? And then what is this number? That's the moment of inertia. Remember I calculated it up there? We rounded it to 21 up there. They used a little bit more accurate value of with 4 digits, which is possible. I have measuring tools in class that can measure to 4 digits easily. So they measured it a little bit more accurately. Instead of rounding to 21, they got 20.8. Okay, so they're using that one. So they're definitely using it in joist mode. You can see the stronger mode. And it's only going to flex 0.12 inches. That's like just almost an eighth of an inch. Not very much. So not very much at all. So if you look at the other calculation, if you go to the next one here, they try ABS, and if you notice everything's the same, 250-pound person standing in the middle, of course, that's the assumption. 96 inches, that's how long the beam is, and then they have to cube it. On the bottom of the equation, make sure you do all this math, and this one you have to times it by 4. Oh, actually, sorry, this one you don't times it by 4. It already has been. This was that one you have to calculate right here. That 20.8 is exactly the same as before. Why is it the same? Because the width and the height is the same. So with the base, what they call it the base and the height are the same. So the moment of inertia is the same. Everything is the same. The only thing that's different is this right here. The material, the modulus of elasticity. It's different material, so it's more flexible. So you got to put that number in. So when you get your answer, of course, it's going to flex more when the person stands on it. Over a half an inch, actually, of flex. So that's the only difference. And I think that's enough. I think if you guys kind of understand that, and you guys can do a little bit of math for me, and just know those terms, joist and plank and modulus of elasticity right here. Modulus of elasticity is the type of material. The moment of inertia, that's the profile on the side right here, that little side cutout. That's what that looks like, and you do a little tiny math for that. And that's pretty much it. Thanks for watching, guys.